All right, dear students, welcome to a new week with new lectures, and we continue in the book with chapter 3, Brownian motion. But before we define Brownian motion, let's first look roughly what Brownian motion is. And in essence, the Brownian motion is a scaling limit of so-called symmetric random walks. So before we go to Brownian motion, let's try to understand symmetric random walks and see their properties. Yeah, we will show you how we can rescale them. And in the limit, we will get Brownian motion, which will have a normal distribution. So let's start with the simple random walk in this section 3.1. And the basic random walk that we know is flipping a fair coin repeatedly. And we have seen that before in chapter 2. And in this case, big omega is the set of all coin flips. Omega 1, omega 2, etc. They can all be head or tail. And the standard sigma algebra, which one takes with omega, is the smallest sigma algebra containing the so-called cylinder sets. And we call it the product sigma algebra. So generated by the cylinders, and these look like this here, right? Omega 1, omega 2, up to omega n. They are all head or tail, and it's omega 1 equal to a1, etc., etc., omega n being an, and each ai is either head or tail. So you look at all sequences, so that the first one is, for example, classified as a head, and etc. So these are all specified ahead of time. And anytime we want to prove something, it's enough to look at sets like this. Yeah, the probability measure P that we are looking at is called the product half-half measure. And in essence, all it does is it looks at how many specified coordinates, if I look at cylinders. And in this case, any head comes with a probability 1/2, and any tail also comes with a probability 1/2. So it is defined as follows, right? Probability of omega 1, omega 2, etc., omega n being given a1 up to an is 1/2 to the power n. Now let's define xj, j larger equal to 1 on omega as follows. And so these are our coin flips. Xj omega, it is equal to 1 when omega j is a head, and it's equal to -1 when omega j is a tail. So omega is omega 1, omega 2, etc. And these are the individual coin tosses. Yeah, and note that x1, x2, etc. they are all independent. And remember from probability theory, these variables are called Bernoulli random variables. They are independent, and they are also identically distributed. And we call that IID. So if my coin is fair, then the probability of any xj being a 1 or a -1, they are all the same. If we are working with a biased coin, with a head comes with probability p, and with a tail probability 1 minus p, then our probabilities will be p, and the other one would be 1 minus p. All right? All right, now I will define my random walk. At time 0, it's going to be 0. Yeah, m0 is equal to 0. And we will define the the symmetric random walk with m instances, m sub n, as the sum j is 1 to m n of xj, of these coin tosses. And the discrete stochastic process, m0, m1, m2, etc., that is called a symmetric random walk. Now, when head and tail, when h and t come with different probabilities, then we may end up with an asymmetric random walk. In that case, we don't have a fair coin, but we may have an unfair coin. Let's start with the properties of the increments. First of all, remember that in essence, a Brownian motion, which we abbreviate with BM here, that is a scaled limit of the symmetric random walks. So therefore, we start with a quick review of the symmetric random walk, and we emphasize their basic properties. Let's start with the properties of the increments. And for that, I need to write an equal sign here. All right, I will improve that in the slides. Let's choose a sequence of non-negative integers, and we see them, and these are m integers, and we see them as m instances in time. 0 is equal to k0, is less than k1, less than k2, up to km. And let's define the corresponding increments of our symmetric random walk m. And there we have mk1 minus mk0. Now with k0 being 0 and m0 being 0, this is just mk1. And that is then defined, if you recall, as the sum I is 1 to k1 xi. The second increment, mk2 minus mk1, that is then defined for I running from k1 plus 1 up to k2 of xi. And see that these are independent of these, right? So this one starts with k1 plus 1, and this one ends with k1. And we continue like this. We make mk3 minus mk2, etc., until we reach the last increment, mkm minus mkm minus 1. And that is then defined as the sum I runs from km minus 1 plus 1 up to km of the xi's. And again, all of these are independent of each other. The second one was independent of the first set. The second increment was independent of the first one, etc., and so on until the last one. Now, even in the case of an asymmetric random walk, the unfair coin, these increments would be independent. And this property will also be preserved when we apply scaling and when we take limits. In other words, this property will be preserved for Brownian motion. Now let's investigate the expectation of the increments. So let's look at the expectation of the increments. The expected value, in this case, the expected value of mki plus 1 minus mki, that is by definition, the expected value where j runs from ki plus 1 until ki plus 1 of xj. And we know that the expectation operator is linear. So we can take the sum out of the expectation operator. So it's the sum over all these expected values. And we know that the expected value of each xj is equal to 0, because we have a probability 1/2 that a 1 is generated, plus a probability of 1/2 that a -1 is generated. It's a discrete random variable. So in total, each of them is equal to 0, and then also the sum is equal to 0. Now let's also look at the variance. The variance of mki plus 1 minus mki. And again, by definition, that is the variance of the sum where j runs from ki plus 1 until ki plus 1 xi. And now what we the step that we do now, we can only do because we have independent random variables xi. Yeah, because we have independent variables. When we write it out, we can take this step. By definition, in general, the variance is not linear, and only in the case that variables are independent, due to independence, we can say the variance of the sum is the sum of the variances. Yeah. Now, these are all Bernoulli random variables. So if you would calculate the variance via the known formula, and so the expected value of x squared minus the square of the expected value, then one part is 0. So the square of the expected values is 0. And the expectation of x squared, that is, well, for xi, we can take the values 1 and minus 1. And if you square it, it will take the value 1 with probability 1. So this first term in that known formula for this first term in this known formula for the variance, that is equal to 1. So it's 1 minus 0, and that's equal to 1. And if I use this information in here, so we have the sum, it's the sum of terms, then I see that this is equal to ki plus 1 minus ki plus 1 times the 1, which makes ki plus 1 minus ki. It is just the number of steps taken in the expression. And sometimes we write this by saying the variance of a random walk accumulates at a rate 1 per unit time step, yeah, per unit step. So the individual ones are 1, then we have the sum, and therefore we end up with ki plus 1 minus ki. All right? Another property that we really like, that is the martingale property. We mentioned that we'd like to price a financial derivative in a fair way, and mathematically fairness is connected to the notion of martingale. So let's look at the martingale property of a symmetric random walk. When we talk about the martingale property, there's always an associate filtration. So let's consider the following filtration, the one that we have seen before. F sub k, it's the sigma algebra carrying the information of the first k coin tosses. So F1 is contained in F2, is contained, etc. in F. So if we know the first 2 coin tosses, then we know the first one, etc. Yeah, so well, the coin tosses are coded, right, with a sequence xi. And notice that the xi carries the same information as the coin toss, right? 1 and minus 1, 1 head and tail. So we just code this, right? Xi is 1 when the event is head, and it's minus 1 when the event is tail. It's just a coding of the outcomes. The ith toss is coded in the random variable xi, and we see that fk is also the sigma algebra generated by the random variables x1 to xk. It is a martingale with respect to the filtration fn. There are 2 properties in order to have the martingale property. There are 2 properties that need to be satisfied. and that is adaptivity. So the process should be adapted, and that is clear. Mn depends on the first n tosses. So Mn is Fn measurable. So if I know in which element of Fn my outcome lies, then I'm able to determine the value of Mn. And we have the measurability, therefore, right? So Mn is adapted to the filtration, and this is precisely the definition of being adapted. The second property is related to the conditional expectation. If you recall the two properties for the martingales to be satisfied. So let's take two instances in time. So m being less than n. So m coin tosses being less than n coin tosses. And we look at the conditional expectation, mn, given the filtration at m. Yeah, so I'll tell you, if I tell you what happened in the first m tosses, and I want to look further, and I look at mn. Yes, and that conditional expectation, if you recall, for the martingale property to hold, that should be equal to m sub little m. To calculate this, we use the same trick that we will always play and that we always play. Yeah, you simply write mn as mn minus mm plus yeah, as a sum of two pieces. One piece depends on m and is fm measurable, and the other piece is independent of fm. So you can do this here simply by looking at mn minus mm and mm. And if you add them together, you see it's just m sub n. Yeah. Note, the sum is just mn. Now, the first part here does not depend on m. It's independent of fm. And this part, the second part, that is fm measurable. And this is a trick that we will often play. Now, we know, we have seen that conditional expectation is linear. So we can break up this conditional expectation into two. It is the conditional expectation of mn minus mm given fm plus the expectation of mm given fm. Right? Now, what we can do is take out what you know, and that is regarding the second term here, the second term. Conditional expectation is then equal to the random variable. Yeah, one part is independent, and the other part is fm measurable. Take out what you know. So this is in essence fm. Yeah, this is in essence fm. And this part is independent of fm. And therefore, this is can be written just as a regular expectation. Instead of a conditional expectation, we can just write this as a regular expectation, because it's independent. Fm doesn't shed any light on Fn of Mn minus Mm. Yeah. And if we write this out, this then is equal to 0. Yeah, the expectation of this increment is equal to 0. That other part, take out what you know, that was mm, and that is equal to mm. So the conditional expectation of mn given fm is equal to mm And that is because Mn minus Mm is independent of this filtration, of this sigma algebra, and Mm is Fm measurable. So we see that the martingale property holds for the symmetric random walk. We can also determine the distribution of the MNs. So you have seen this, but we will repeat it here in a remark. Yeah. The distribution of the increments is easy to find. First of all, the distribution is discrete. So I have done here n min minus m steps. Yeah. So the first one doesn't really count. N minus m steps. Now I've reached level y. So what is the probability that mn minus mm is equal to j? What is the probability that I have reached level j? And we do that here. So this is additional information. Just let's compute it. We know we are dealing with Bernoulli random variables, right? The distribution is discrete. Let u be the number of upward steps. Let u be the number of upward steps, the number of ones. And let d be the number of downward steps, yeah, the number of minus ones, the number of minus ones. Then mn minus mm equal to j. That tells us that the number of upward steps plus the number of downward steps, that is the number of total steps. U plus d is equal to mn minus m. Then moreover, u minus d, that is then equal to j, the value it has reached. U minus d should be equal to j. The number of upward steps minus the number of downward steps gives you the number we have reached. Now, these are two equations with two unknowns. We can just add them together. This one plus this one gives us 2u. The d cancels out. 2u is equal to j plus n minus m. And that gives us, of course, that u is equal to j plus n minus m over 2. And if we have this, then we also know d. Of course, we know our d. d is then equal to j plus n minus m over 2 minus j. So it is d is u minus j. So this is u minus j. And that is then n minus m minus j over 2. And with this, we can compute this probability. The probability that mn minus mm is exactly equal to j. That is the total number, n minus m over the number of j's or the number of d's. And that doesn't really matter in this case, in this symmetric case. So that is n minus m minus j over 2. And of course, that is then the number times the probability, and that is 1/2 to the power n minus m, because we have a fair coin and the number of upwards is equal to the number of downwards. So this goes with the power of the total number. So this first part again is how many ways can I reach level j? Yeah, how many ways can I reach level j? And we have seen that in order to get to level j, we have to make n minus m plus j over 2 upward steps and n minus m minus j over 2 downward steps. So from the total n minus m steps, we have to choose n minus m plus j over 2 steps upwards, and automatically this will tell you the total number of steps downwards, adding the number of up and the number of downward steps. In total, we will make n minus m steps. Regardless up or down, because it's symmetric, it comes with a probability 1/2. And so this is the probability, the discrete, had a probability in this distribution of these discrete increments. Now let's look at another property that we will also find important, and that is the concept we call quadratic variation. Yeah, for symmetric random walks, this is a trivial concept, but it's very relevant for a Brownian motion. Let's have a look for the simple case. The symmetric random walk, m, mn, n greater or equal to 0, let that be a symmetric random walk. Now we define the quadratic variation, which we abbreviate with QV often, at time n as follows. So m is this m and m in square brackets sub n, and that is the sum from j is 1 to n of the increments mj minus 1 squared. Yeah, so again, the quadratic variation denoted by this expression with the square brackets is the sum of the square increments. And by definition, this is a random variable. And it's obtained by taking the sum of the increments squared, a random variable. But in this particular case, it leads us to a constant. Why? Well, because when I write this, formally this is a stochastic process, but if I write this out, this summation, again, I'm squaring xj here, and we have seen that this is in essence a sum. J is 1 to n of 1. So if I square xj, we have just seen that that is in fact, it's a 1 or a minus 1. So it's always 1. In the square value is always 1. It's a sum of ones, and n ones makes n. Yes. And this is exactly the sum from j is 1 to n of the variance of xj. That is equal, in this case, to the variance of mn. Yeah. So it gives us n, it's a constant in this case, and it's equal to the variance of mn, only in this case. Yeah, and that is what we wrote here. But again, this is a very special case. Variance involves expectations, so it's an expected value. You average along each path. But the expression I wrote at the beginning, the sum of the squared increments, it is a random variable. So the random variable appears to be a constant here. In general, this need not be true. Yes. So now we have understood quite a few properties of the symmetric random walks. We have seen independent increments, zero expectation, variance equal to the time interval, and the quadratic variation equal to the time interval as well. And we have seen the martingale property. Now let's go one step further and see if we can rescale such things. So we're going to look at a scaled symmetric random walk. A scaled symmetric random walk. And this is actually what one does when one simulates a Brownian motion. So we take already a step towards simulation, implementation in a computer. We will see that a little bit later on. But the symmetric random walk also forms the basis for the numerical simulation of a Brownian motion. So this is the process that we use to build a Brownian motion, really. Yeah. So given a symmetric random walk, m sub n, n large equal to 0, then for each n larger equal to 1, the so-called scaled symmetric random walk, a continuous process, is given by the following expression, w superscript n. So we give it a superscript to explicitly denote that that it's fixed n. Yeah. Therefore, we give it a superscript. Now I scale it with step square root of n. So I multiply by 1 over the square root of n. This m, our independent increment. And I scale time. So time is scaled. It's n times t. So time is stretched here. Because m is originally indexed as by a discrete time n, and n need not be an integer. So to be exact, we write that we provide nt to be an integer. Yeah. So we provide n times t to be an integer. And we linearly interpolate between integer values. N is fixed, t is the parameter. So this gives us, in fact, a continuous time stochastic process. Yeah, we scale time by a factor of n, and we scale the step size by a factor of 1 over the square root of n. So before we look at limits, let's first investigate this process. Yeah. N is fixed, n times t is changing. So from the definition of Wn t, assuming nt is integer, if I replace this value, I'm still working with a random walk, but I've multiplied it by square root of n, and the properties essentially remain the same. The increments, for example, Wn, the increments Wn at ti plus 1 minus Wn at ti, that is just defined as 1 over the square root of n. And now the sum, j, runs from nti plus 1 to nti plus 1 of xj. Yeah. So this process, Wnt, for t non-negative, is defined as follows. Yeah. And the increments, they go like we would expect they would go. Now again, the properties remain the same. Yeah. We have different indices, right? We have n times t, I, and n times ti plus 1. We have different indices, but we see that still all these increments, they will be independent. We still see that the expectation is equal to 0. Yeah, there's no reason to assume differently. The sum of expectations, each one is equal to 0. Well, when we look at the variance, then we have to be careful with the brackets. So we first substitute the definition of the variance of Wn ti plus 1 minus Wn ti. That is the variance of 1 over the square root of n, j running from nti plus 1 to nti plus 1, xj. And now we remember that if we have a scaling factor within the variance operator, then it comes out of the variance operator squared. Recall the basic properties from probability theory 1. So this gives us a 1 over n. The sum, j runs from nti plus 1 to nti plus 1 of these individual variances of xi. And we know this, right? Let me think. Yes, this is, of course, again, the length of the interval. And the length of the interval is nti plus 1 minus nti. N times ti plus 1 minus n times ti. We can take the n out, divide by n, and again we get the length of the interval, the length of the time interval. Ti plus 1 minus ti being the variance of this scaled symmetric random walk. Yes? Now, if we look at the filtration, FM, the filtration is, of course, the first m tosses. And we describe it for each m. And the process, Wm is discrete, but because I'm interpolating, I will make Ft in Fm if t is between m and m plus 1. And then we can see that the filtration is just the sigma algebra of x1 to xm, right? And in fact, again, what we can also prove is that Wn(t) for t non-negative is a martingale with respect to this filtration. So Wn is a martingale with respect to the filtration Fn, the sigma algebra composed of x1 to xn, which is non-negative. So a last thing before we start with the formal definition is the central limit theorem, CLT as we sometimes call it. So Wnt converges to the normal distribution with mean 0 and variance t. And let me emphasize, it converges in distribution as n goes to infinity. So in limit n to infinity, the probability that Wnt is less or equal to x will converge, that's what the central limit theorem says, will converge to a standard normal distribution with expected value 0 and variance t, and that is given by this expression, the integral from minus infinity to x of 1 over the square root of 2 pi t e to the power minus 1/2 u squared over t du. So again, this converges in distribution, and for each fixed t, Wn converges as n goes to infinity to a random normal variable with mean 0 and variance t. So by this, we have given a way of constructing the Brownian motion. So next lesson, we will define Brownian motion formally, but we will repeat a lot of things we have done here. So in the case of formally describing Brownian motion, we will also look at the increments, at the expectations, the variances, etc. There will be technical details, but the ideas will go through for Brownian motion as well. So see you in the next lecture.